Hi everyone, so here I am, Physics Part B study guide. So I'm going to go through every single question just like the last study guide video. Please make sure to follow along with me and to fill out your study guide. A lot of us didn't have time in class to get the full study guide done together, so we're going to do it this way. I think I actually like this way, and I bet you guys do too. So let's go on and get started. So number one says, what is energy? So energy is just the ability to go about your everyday tasks, so to do work and to cause change. So like I have a stapler on my table. In order for me to staple this sheet of paper, I have to apply some force. In order for me to be able to apply some force, I have to have energy. And the energy that's currently fueling my body came from my lunch. So energy allows us to do work and cause change. That's number one. Number two says, what is heat energy? So when you warm things up, your molecules begin to move really, really quickly. And when things start to cool, the molecules start to slow down. So heat energy is just the transfer of thermal energy. So on your test, it's not going to say what is heat energy. Instead, it's going to say what is thermal energy. And you have to know that thermal energy is talking about the movement of molecules, and the faster they move, the higher the temperature, the warmer they feel. And then also, the slower the molecules, the colder they feel, and the slower the molecules are moving. So, number three, complete the sentence. The faster the molecules move, the higher the temperature. So, if they're moving really, really quickly, they're creating lots and lots of heat. So, think about when you guys go outside to run your pacer test. When you start running and you're on a roll, you're just running, running, running. You're creating a lot of body heat. So then when you finally come to a stop, you're warm and then you have to cool down. And then eventually that body temperature that's risen will then, of course, decrease and it's going to lessen, but it's going to take some time because you've worked up so much energy, you've used so much energy, you've done so much work, so your body temperature is increased. So number four, what is electromagnetic energy? So electromagnetic energy is talking about energy that travels in waves. So gamma rays, X-rays, light. So I have light in this room right now because of rays that are traveling through space. So on your test, it's not going to say what is light energy or give me an example of light energy. It's going to say what is electromagnetic energy. And you've got to know that it's energy that travels in waves in the form of visible light, electromagnetic rays, gamma rays, all of those different types of rays and waves. Number six, number five, what is chemical energy? So chemical energy is stored in bonds. So in class, I use the example of making bread. If I have to make bread, I need flour, I need salt, I need baking powder, I'm going to need some eggs. And when I mix all of those items together, they bond. So that when I put them in the oven and then I take them out, it's going to be a loaf of bread that is a combination of the flour and the eggs and the baking powder, all the things that came together to make that loaf. It's not going to be here's my flour and here's my baking powder and here's my eggs. Everything's going to be bonded together. And inside of those bonds of molecules, that's where I find energy. So as we're breaking down food in our bodies through that digestive system, we are storing energy for our bodies to use later. So it's a very important part to know that the chemical energy is actually stored. So it's stored energy in bonds. And as those bonds are broken down, it's stored within you, and then you're able to convert that chemical potential energy into kinetic energy, which is the energy of motion. All right, number seven. No, I'm just skipping all around, guys. I'm so sorry. Number six, what are the three sources of chemical energy? So the ones that we talked about in class are like batteries. Batteries have chemicals in them. Remember, I showed you those corroded batteries that had the acid that was coming through the casing of the battery. Batteries are stored energy, so they have potential energy. Then food, the foods that you eat. As soon as you ingest food and your body is able to break it down, it stores energy for you to use. And you may not use it as soon as you eat it, but your body over time is going to use that energy to allow you to do work, to move some distance, to apply some force. And then lastly, like gasoline. So think about it. When your parents go to the gas station and they fill up a huge tank. Like I have a small little Honda HRV. So I take 12 gallons of gas to fill it up. And once I put those 12 gallons in, I can ride for like a week, week and a half, depending on how far I'm going. So that's stored energy in the form of chemicals in my tank. It's going to propel my car forward to get me here to see you guys every day at school and to also do the other things that I need to do. So gasoline, food, batteries, those are all good examples of chemical energy stored in bonds. All right, number six. Nope, number seven. What is electrical energy? So electrical energy is energy that travels in a loop-like path, but it's through the flow of electrons. So electrons are negatively charged particles. So when we think about an atom has three parts: protons, neutrons, and electrons. So your electrons are on the outside of the orbit of the orbital. You'll learn all of this next year in chemistry, but those electrons are also what runs through our electrical circuit. So it goes from the negative side of our battery once it's connected, or from the negative part of our electrical wiring and like our outlets at home, goes from the negative through the circuit and then back to the positive through the low, whatever is receiving that energy of the resistor, and it keeps flowing a loop like path. So you've got to know electrons flow through an electric circuit. All right, number 8. What is mechanical energy? So we're going to pause here for a second. When we're talking about potential and kinetic energy is stored, kinetic energy is the energy of motion. But there are different levels of energies, there are different types of energy that fall underneath those categories. So potential energy, you find chemical energy, it's stored energy. When we're talking about kinetic energy, you have something like electricity that's always flowing. Mechanical energy is a combination of the both of those. So when I have, say, a stapler sitting on a ledge, because of its distance away from the ground, because of its height, because of its position, it is storing energy. And due to its position, it's going to store a specific amount of energy. So if, say, I were to drop this stapler, okay, I'm going to drop this. As it begins to drop, the potential energy that it stored while it was sitting on my hand is now being converted into kinetic energy as it falls. So mechanical energy is potential energy plus kinetic. When the stapler is sitting here on my hand, it's not moving at all. So it has 100% kinetic energy. So let's say 20 joules of energy. And it's going to have 0 joules of kinetic energy because it's not moving. So when I add that 20 plus 0, that's going to give me a total of 20 joules of energy. That would be this object's mechanical energy. Now, say I were to raise this stapler up. As I raise it further and further up, that means it's going to store more and more energy. So then that means as it falls, there's more energy that can be converted into kinetic. So when we want to raise the amount of mechanical energy an object has, we have to raise its potential energy. So I have to increase its distance. So the further it is, the more energy it can store. And as it begins to fall, what happens is my stored potential energy becomes the energy of motion, which is kinetic. So you've got to know that mechanical energy is due to position, so potential energy, plus energy of motion, which is kinetic. So it's a combination of both position and motion. So number 9, what is the formula for mechanical energy? Kinetic energy plus potential energy equals mechanical energy. Number 10, what is potential energy? It's stored energy. It's energy stored in any type of object, depending on its location and position. It's in bonds, like chemical energy. It's just energy that's not currently in motion. It has the ability to one day or at some point be in motion. It can cause some change. But right here, right now, wherever you are, if something is not moving, and depending on its height, it's storing energy to be used later. And number 11, what is kinetic energy? So it's energy that's been transferred from potential to kinetic. So the kinetic energy is the energy of motion, and it relies on the stored energy that an object had before it was in motion. So like the stapler on my hand, stored energy, and as it falls, this stored energy will transfer to kinetic energy over time. All right, number 12, what is the law of conservation of energy? So that law just states that energy is not created nor destroyed, but instead it's just transferred. So going back to my example with the stapler, as the stapler begins to fall, what happens is the potential energy turns into kinetic energy. So we didn't create any new energy as this fell, and we didn't create any energy as it was sitting on the ledge. Instead, those energy sources were transferred from one place to the next. So like think about an apple that you eat. That apple that you eat at lunchtime is giving your body energy. But before it made it to your mouth, digest into your body to give you stored chemical energy, there was a plant somewhere, there was an apple tree somewhere that received sunlight that allowed it to grow. And then as it grew, it was picked. And then eventually, through some other steps, it made it to you. So originally, the sun was the driving source of energy to allow that apple to grow and then get to you. So we didn't create the sun, but most of the energy that we use originated from the sun. So a lot of our energy sources all come from the sun in some way, shape, or form. which is pretty cool. So, law of conservation of energy. Energy is neither created nor destroyed, but transformed from one form to another form. All right, and number 13, most of the energy that we use on Earth originally came from the sun. Okay, section 2, kinetic and potential energy. So all we're going to do here is we're going to classify the following as a type of potential energy or kinetic energy. Use the letters K or P. So remember, potential energy is stored, and kinetic energy is the energy of motion. It's going to change position over time. Number 1, a bicyclist pedaling up a hill. So if I'm pedaling, I'm moving, okay? So I'm probably using, well, I am using some of my stored energy depending on where I am, but I am in motion, so I have kinetic energy. Number 2, an archer with his bow drawn. So if the bow is just drawn and the bow hasn't actually left the archer just yet, it's stored energy. So I'm storing some elastic energy as I pull it back. And then when I let it go, then it will have kinetic energy, but not until then. So if I'm just drawing it back, it's going to have potential energy. Number 3, a volleyball player spiking a ball. So when you're spiking a ball, you're applying some force to a ball that is in motion. All right, so that one's going to be kinetic. Number 4, a baseball thrown to second base. So we did this one in class. When a ball is thrown, you're applying a force to it, and it is going to move some distance. So it's kinetic energy. Number 5, the chemical bonds in sugar. So the bonds in sugar, once they're digested in your body, are going to give you energy, but not until then. So there's stored energy in that sugar. So every little thing that you're going to eat has stored energy in it. And that's why we're choosy, well, we're very selective about what we eat, because depending on the different foods you eat, you get different amounts of energy. Like if you eat a cereal bar, I don't know, that's loaded with sugar, you're going to get some energy from it, but it may not last you as long as, say, a hearty bowl of oatmeal that's full of different vitamins and minerals, and healthy combinations, healthy compounds that are going to power you for the rest of the day. So, depending on the type of food, you're going to get more energy depending on what it is, the quantity that you're eating, and so on and so forth. But just know, food is potential energy. Number 6, the wind blowing through the air. So we know wind is moving air. So because the wind is moving, it is kinetic, people. All right. Number 7, walking down the street. If I am walking, I am moving. So that means that that person is going to have kinetic energy. Number 8, sitting in the top of a tree. So if I'm just sitting in the top of a tree, because of my height, the distance I am away from Earth's surface, I am storing energy. So I have potential energy. Okay. Number 9, a bowling ball rolling down the alley. If it is rolling, it is moving. And if it is moving, it has kinetic energy. 10, a bowling ball sitting on the rack. If it's just sitting on the rack and it's not moving, it has potential energy. And it has potential energy, A, because it's not moving, and B, because it's sitting on a rack that has some distance away from the floor. So remember, potential energy is due to height. So the further I am from Earth or from the surface or from the ground, the more potential energy I can store. Page 2, people, page 2. So now we're moving on to energy transformations. So what we're trying to do is figure out, so we're going to read the scenario. And as we read the scenario, like we did in class, we're going to try and figure out what was the initial source of energy and how is it transferred over time. So number 1 says a battery is placed in a flashlight. So we know a battery is chemical energy. Bingo, easy. Which completes a circuit. So circuits are electrical, then produces light. So light, this would be radiant / electromagnetic. So remember, light travels in rays. So rays are going to be electromagnetic energy for number 1. Number 2, a rotating turbine generates electricity. So a turbine is kind of like a windmill. We did an example like this in class. So a rotating turbine generates electricity to power a blow dryer. So the first thing is a rotating turbine. A rotating turbine is going to use potential energy to begin with. That says potential over here. So this is potential energy. So there had to be some stored energy before that turbine got started. And then once that turbine began to turn, it's going to convert that potential energy into kinetic energy. So that's potential plus kinetic. So that means it's mechanical energy. And then as the mechanical energy is being used, it's going to typically create some electricity. So that's electrical energy. And that electrical energy is going to power a blow dryer. So a blow dryer is going to create some thermal energy. You could also say sound energy. Number 3, lion on a cliff's edge. So if he's on a cliff or they are on a cliff's edge, then they're storing potential energy. It doesn't say they're running on the edge of a cliff, which probably wouldn't be smart. But anyways, so they're storing gravitational potential energy. So gravity's pulling them down, but because of their distance away from the Earth's surface, they're storing potential energy because of height. So their potential energy, as it pounces, going to become mechanical energy. So potential energy is going to transfer to kinetic. So potential energy plus kinetic energy becomes mechanical energy. And then using that mechanical energy, it's going to pounce onto a deer and consume it. So as it's consuming, it's going to get chemical energy from the deer. Poor Bambi. Number 4, electricity flows to microwave as it reheats your food. So first thing, electricity is electrical energy, and it's going to flow to the microwave. So electricity is going to allow mechanical energy to happen as the microwave is heating your food, as it's spinning, as the waves are moving. So potential energy, kinetic energy gives you mechanical. And then it's reheating your food. So it's reheating that chemical energy that's going to fuel your body or whoever's body that's about to consume it. Number 5, a person standing on the edge of a diving board pushes down to bend the board, then bounces up. So the first thing is, if I'm standing on a diving board, I am not on Earth's surface. So I am some distance away from it. So I'm storing gravitational potential energy. Then the board is flexible, and because it's flexible, it has elastic potential energy. So as I'm on the board, kind of pushing up and down, I am using elastic. Well, I am storing elastic potential energy. So it's kind of giving me some momentum here. And then as I jump off, I'm using mechanical energy. So I'm transforming my potential energy, which was stored, to kinetic energy. Number 6, Apollo 13 is preparing to take flight. What types of energy transformations take place as the spacecraft takes off? So first thing is, this spacecraft had to have energy of some sort, and typically it's going to have gas. Gasoline, remember, is chemical energy. So the chemical energy is then going to power all the electric units inside of that spacecraft. So chemical energy is going to be transferred to electrical energy. And then from the electrical energy, we're going to get thermal energy, because think about the explosion that's happening underneath. The chemical reactions are happening and it's creating heat. And then just remember, chemical energy is stored energy, so it's potential energy. And then electrical is kinetic, and thermal is also going to be kinetic, because these are both two types of energy that are moving. So overall, the kinetic energy is increasing as the spacecraft takes off, because stored potential energy is being used to power the electricity so the electrons can flow, and the thermal energy so we can have those chemical reactions, so that the spacecraft can actually take flight. So kinetic energy is increasing. All right, so looking at our pendulums here. So label the diagrams below to indicate the position in which the ball has the greatest and least amount of kinetic and potential energy. So let's start with number 11. So number 11 is kind of like our Newton's cradle that's in our classroom. So this is like when I pull the ball back. So we're at A. So when I pull my Newton's cradle ball back, that's storing energy. And as I let it fall, so it's pulled back at A. So this is where I'm going to have the highest potential energy because of its height. So if you compare A and G with the rest, this is the highest point. So because of its distance away from the ground, away from the surface of Earth, it's going to store energy. Because remember, potential energy has everything to do with its position or its height away from the ground. So I have my highest potential energy. And remember, wherever I have my highest potential energy is also going to be where I have my lowest kinetic. But as I let my ball go and it starts to travel, what's happening is my potential energy is going to turn into kinetic. It's going to transfer. So when I get halfway between A and D, so somewhere between B and C here, there's going to be half kinetic and half potential, because I've lost half of my potential energy because it's converted to kinetic. And I still have another half. But as I make it down to D, and that's the lowest part on my pendulum, that's going to be my highest point of kinetic energy, because at this point, all of my potential energy would have transferred into kinetic energy. So I am in motion. So I'm moving at this point. So, but then as I travel back up the pendulum, I'm starting to lose kinetic energy because of height. So as I move upwards, I'm losing kinetic. So then my potential energy is increasing. So as I travel from D to E to F to G, I am losing kinetic energy, but it's also being just transferred back into potential energy. And it's just going to go back and forth, back and forth. All right, number 12. So I have a picture of, I'm going to assume this is a roller coaster, I think. So when I'm at A, this is going to be where my potential energy is going to be highest, and it's due to height. This is the largest part. This is the tallest part of the trip. So A is going to be the highest point of potential energy. And as it starts to move down, the potential energy that's stored is going to turn into kinetic energy of motion. And as it gets to be here, this is going to be one of the highest points of kinetic energy because it's in full motion. All the potential energy would have transferred into kinetic. But as I start to travel back up this loop because of height, my kinetic energy is going to decrease and my potential energy is going to increase again. So this would be the second point of highest potential energy. So A is the highest, so that's the highest point of potential energy, but C is a close second. So as it travels down C, then the potential energy is going to decrease because of height, because we're getting closer to the ground again. And then at B, my kinetic energy is going to be highest again. Then as I keep going through my trip, every time I increase my distance away from the ground, potential energy is going to increase. But as I travel back down, it's going to decrease. All right. So let's move on to our roller coaster here. So with our roller coaster, just note the roller coaster will speed up as the potential energy exchanges to kinetic. So when I'm on this roller coaster, think about like when we went to Carowinds a couple weeks ago. We traveled all the way up those really big hills at the beginning of rides to build momentum, to build our potential energy. Because after we get going, that potential energy that we stored at the beginning is what's going to give us our momentum to travel through the ride. Because if we don't store enough potential energy at the beginning, then I'm not going to be able to have enough potential energy at the end. So I'm going to make a little drawing real quick. So let me find a marker. All right. So I have two pictures. Hopefully you can see this. So I have a picture where my cart is starting some distance away from Earth's surface. There's quite a bit of different distance. So I'm storing potential energy. The stored potential energy is then going to give me enough energy to travel through my journey here. But I also have another picture. Now with this picture, I don't have enough stored potential energy to make it up here. So because I'm starting out so low, I'm not going to be able to finish my trip. I'm probably going to get stopped somewhere right in here. So it's important when you're on a roller coaster or you're looking at a problem on your test, I have to store enough potential energy at the beginning in order to have enough momentum to make it through the rest of the trip. So it's important. The starting point is very important. All right, now to the questions. So it says, as you move up to the first hill, so we're moving up the first hill here, okay? On a roller coaster, the distance between the coaster and the earth is going to increase because if I started down here and I'm moving all the way up here, my distance is increased. So I've gotten further away from the ground. So the potential energy, well, the coaster is going to increase its distance away from Earth's surface, resulting in an increase in potential energy because of its height, I'm storing potential energy. Number two, at the top of the first hill, you have the highest gravitational potential energy because of its height. So it's far away from Earth's surface. It's the tallest point in this ride. So I'm storing the most potential energy. Number three, so as you begin your trip down the hill, though, you're going to increase your speed. So you're going to go faster because gravity is pulling you down. And as gravity is pulling you down at 9.8 meters per second squared, what's going to happen is your kinetic energy is going to increase. So let's move on to number four, I think. I don't know. So as you begin your trip down the hill, you increase your speed, resulting in a transformation from potential energy to kinetic. So the stored energy that I had at the top of the roller coaster, so like our example here, stored energy that I had here is going to transform into kinetic energy as I start to travel down because I'm in motion. And it's going to allow me to move through the rest of my trip. So number five, at the bottom of the hill, right before it goes back up. So like at the bottom of the hill, I have kinetic energy of motion because I came down here. But as I'm moving back up, I'm going to start losing some of that kinetic energy and it's going to turn right back into potential energy. So at the bottom of the hill, right before it goes back up, where the kinetic energy is high. So it's high at that point. But the kinetic energy transfers the potential energy as the car travels up the loop. So looking at our picture, down here, our potential energy is low and our kinetic energy is high because of its distance. So I'm storing energy up here, and now it's energy of motion down here, so kinetic energy. But as I travel this loop, my potential energy is going to increase here, but it's going to decrease as I move down my loop. So lastly, as it starts to move up the next hill or loop, kinetic energy is transferred back into gravitational potential energy. So as I travel this loop and travel up it, and I get to the top of the loop, I'm going to gain gravitational potential energy and lose kinetic energy because it's transferred. All right, section number 4. So I have a picture of a circuit. This is a series circuit, and it's a series circuit because everything is connected. So I drew some additional arrows in here to show that your energy starts at the negative part of the battery, and it's going to go to bulb 1, bulb 2, to the switch, and on around. This is what we call a series circuit because they're in series. Bulb 1 receives energy, then bulb 2, and the switch is going to turn the energy on or off depending on if it's open or closed. This is an example of a closed circuit because everything is flowing. Everything is able to receive energy. That's why these lights are bright, because everything's nice and connected. Now, if this switch was open, then energy would not be able to flow. So number 1, trace the path of the electrons in the series circuit. So like I said earlier, it's going to go from the negative to bulb 1, bulb 2, to the switch, through the wire, and back to the battery. But it's going to end up at the positive sign and then come right back out on the negative side to allow the lights to still emit light. Number 2, in this circuit, the electricity has one path. There's only one path. It's going to come from the negative to the bulb, to the switch, and back. There's only one path. Number 3, the circuit is complete. It's going to be complete because the switch is not open, and also because both the negative and positive sides of the battery are connected. Number 4, where does the electricity have to go before it reaches bulb number 2? Well, it has to go through bulb number 1. So that's the problem with the series circuit. Remember I told you about my house when I was a kid? Everything was wired on a series circuit. So when I turned on my lights in my room, everything turned on. And then when I turned off my lights in my room, everything turned off, which was a pain because you had to dim the lights in order to watch TV in the dark, which was absolutely crazy. But series circuits, everything's connected. So if one bulb goes out, everything goes out. So that's kind of the negative side of series circuits. So number 6, if bulb number 2 were to go out, bulb number 1 would go out. That is true because everything's connected. So if energy cannot pass through bulb number 1, then it's not going to go through bulb number 2. Now, if it can go through bulb number 1 and gets to bulb number 2, energy is going to be stopped here. So it doesn't matter which bulb goes out. Regardless, neither one's going to receive energy because it's not going to be able to flow in a loop-like path because it's kind of like a big stop sign. Energy can't flow anymore. So neither of them would emit light because it has to be able, the electrons have to be able to flow through the current from negative to positive. All right, number 7, in this circuit, each bulb is not getting the full electrical pressure, and that's because half of the energy, half of the electric current is going to bulb number 1, the other half is going to bulb number 2, so they're sharing the electricity. Now, if we were on a parallel circuit where there are multiple paths, then each one could have a full amount of electrical energy. Say we turn off bulb 1 and we just have bulb 2 on. But in this circuit that we have here, they're sharing the electricity between the two. All right, let's see. Number 8, if more bulbs were added to the circuit, each bulb would give off less light. And it's going to be less because they're sharing it. So the more lights you add, the less light they're going to have. So it's kind of like during the circuit lab, some of you were able to attach like 3 or more holiday lights. And with those holiday lights, as you were adding them onto the series circuit, like if you were to just put on the alligator clips all 3 of the holiday lights and the battery together, all 3 were dim. And as you took them off, you were able to see that the lights were getting brighter and brighter and brighter. And that's because the electric current was shared between all 3 bulbs when they were together, then 2, and then when it was just 1, it received all the electric current that was coming from the battery. All right, number 9, if this circuit had only 1 bulb, it would give off more light. I forgot to fill that in, but it would be more, and it's going to be more because only 1 bulb is receiving all the volts of energy, all the electric current that's being passed. All right, so identify if the circuits below are in series or parallel, and if they are open or closed circuits. So both of these are going to be closed circuits. The switch is closed here. Well, no, actually, this one is closed because the switch is closed, and energy is flowing from the negative to the positive, and the light is on. So this is a closed circuit, and it's also in series. So if this light went out, then of course, well, it's only one light, but still, say we added a second light to this, then if one went out, the other one wouldn't receive electric current. So this is a closed circuit because the switch is closed. So remember, if I have a closed circuit, my electricity is flowing. If it's open, it's not. So that's what's happening in our schematic diagram here. So the switch is open. So if the switch is not lying flat, typically that means it's open and that means electricity is not flowing. So when it is closed, that means that my electric current is flowing. So you always want a closed circuit if you want electricity to flow. If you don't want it to flow, that's when you open it. So it's like with a light switch. When the light switch is on, that means the circuit is closed. Everything is working together, everything's connected. When the switch is open, that means that light and electricity is not flowing because everything is not connected. There is a break in one of the circuits. There's a break in the flow of electric current. So it's really important that you know this little symbol. So the long line with the smaller line, this represents your battery. That is a test question. Make sure you know that this is a battery. This is also a bulb symbol. That one's a little easier to remember. And then this one is a switch. All right. So simple machines. So remember, you have 6 simple machines. The first one is a lever. Remember, a lever kind of looks like a seesaw. So you have what we call a fulcrum. So a fulcrum is kind of like the middle support, and that's what allows your bar or beam to rotate. So it pivots on top of that bar. So when you're trying to move an object on a lever, you want to move your fulcrum in the middle closer to the load because the more effort arm you have, the more ability you have to move it easier. Whereas if I move the fulcrum closer to the load, that reduces the amount of effort arm I have. So I want to have a long effort arm to move my load. So a lever is made of a stiff bar that rests on a fulcrum. The bar is the part of the lever that moves, and the fulcrum does not move. So examples of a simple machine are like scissors or a seesaw. So remember, fulcrum, that's our word there. The fulcrum is kind of like the point of support. It's like our fixed point that allows our bar and our load to move. All right, so an inclined plane. Remember, it's kind of like a ramp. So it has a long hypotenuse. It has a steep, well, it has a less steep slope than, say, going up a stair. Okay, so if I'm going up a staircase with a person with a wheelchair, that's going to be very difficult and require lots of energy and work. Whereas if I take them on a ramp, I'm going to increase the distance that I travel, but I'm going to decrease the amount of effort that I have to apply. All right, a wedge. So wedge is there to separate things, to pierce things. So a wedge is made up of 2 inclined planes that form a sharp edge. So a doorstop and an axe are examples of wedges. And also wedges help to change the direction of force. So like if I push a door open, like the door at the back of my room, as soon as I push a door open and I'm no longer applying that force, it wants to close back automatically. But if I put a wedge underneath the door, it's going to change the direction of force. So as it's closing back, if I put a wedge under the door, it's going to push it forward and it's not going to be able to close. So wedges also help to change the direction of motion. So a screw helps to fasten things or hold things together. You find screws in everyday appliances. Even your cell phone has a screw in it. And it's made of an inclined plane with ridges or spirals wrapped around it. And it's not like a nail because when you use a screw applies friction between 2 objects and it helps to hold them together better. All right, and then a wheel and axle. So just like a car. So a car has 2 wheels, and those wheels are going to rotate around a metal bar in the middle called an axle. So it helps to move things. And as you're using a wheel and axle, it's easy to transport things from one place to the other. All right, and this little note, just so you know, goes down here. So lastly is a pulley. So a pulley is made up of wheels and a rope. So what happens is the rope goes over the wheel, and as you pull it, it's going to help move an object. But the good thing to know is when you apply a force to a pulley, say I want this bucket, or I don't even know what that is. I just drew something. Say I want this object to go up, then I'm going to pull this rope down. So when you are using a pulley, it's going to change the direction of effort applied by the person. So as I pull down, the bucket's going to go up. And as I allow the rope to go back up, the bucket's going to go down. So a pulley helps to change the direction of effort applied by the person. It's also as a person pulls down, the object's going to go up. And the more pulleys I add to a system, the less effort I apply. It gets easier to move an object. So it's kind of like in class when I had those three 1,000-gram weights. When I had just one pulley, it was difficult. It's like a workout to move the weight up and down. Then when I added two, it became less strenuous. And then when I added three, oh, it was pretty easy. I could do without applying much effort at all. So pulleys help change the direction of force. And then the more pulleys you add, the less effort has to be applied. And they're just a wheel and a rope. All right, so mechanical advantage. So mechanical advantage just means if I use a machine, it's an advantage to me. So the person applying the force, applying the effort, can reduce those two things if I use a machine. So they reduce the amount of effort needed to do work. All right, last page, I believe. So this is an example. Sorry, it's blurry. This is an example of a series circuit. So remember, series circuits have one path for energy. So it has to flow in a loop. There's no other way for it to flow. And then just so you remember, parallel circuits have multiple paths. So in this picture, I have a battery. I have a switch that's open. So remember, if I have an open switch, energy is not flowing. And I have a bulb. So this one doesn't have like the little lines around it to show you that it's lit up because it's not, because the switch is open. Remember, open switches do not allow electric current to flow. All right, D. So is the circuit complete or incomplete? It's incomplete because the switch is open. When the switch is up or open, energy is not flowing. Number 4, are electrons moving? No, the electrons are not moving because the switch is open. It cannot flow in a loop-like path because there's one part of the switch that is not connected. Number 5, does the bulb light up? Nope, because electrons cannot flow. All right, so moving on to our parallel circuit. This is a parallel circuit because there are two paths. So I use two colors, orange and yellow. So my yellow is going to bulb 1 and back. So it goes from the negative to the switch to the bulb to the positive and then a loop-like path. But then the orange one, the dots, is going to go from the negative to the switch to bulb 2 to bulb 1 and back. So now it's lighting both. So there are multiple paths in a parallel circuit. And also this one's going to have electricity flowing through it. The electrons are able to flow because the switch is closed. So remember, closed switch means I'm going to be able to have electricity flowing. Open switch, no. So number 10, how many loads does this circuit have? So loads are what's receiving the electric current. So there are two. You have bulb 1, bulb 2. Number 12, is the circuit complete or incomplete? It's complete. The switch is closed. The negative and positive parts of the battery are connected. There's no break in the wire. So yes, it is complete. Last thing, energy does not flow when a switch is open. I can't say that enough. So open switch, no energy. Closed switch, yes, I do have energy. I feel like I was like the genie doing that. But okay, I hope this helps. Tutoring is Wednesday morning at 8 a.m. A-Day, you're testing on Friday. B-Day, you're testing on Thursday. And you guys did so well on the last physics test. I feel like you're going to do just as well on this one. All right, bye-bye.